Welcome everybody to today's video. It is on solar cells. What do solar cells have to do with infrared astronomy? I'm trying to convince you of that. There are some technical common processes, and maybe we can learn from solar cells about photoelectric sensors. That's the only reason why I did this video. I tried to understand how the things work, and maybe the solar cells can help us a little bit. So it's gonna be quite a technically heavy video. First, I'm gonna show you the basic principles of solar cells, and then some problems that silicium-based solar cells have, and maybe the solutions will help us also a little bit for camera sensors. But the main topic here is solar cells. I will just compare a little bit here and there with photographic sensors. How do solar cells work? The sun is shining on a semiconductor, and the semiconductor has two halves, but they're connected actually, an N-type and a P-type. N here stands for negative and P stands for positive. So the solar cell is more or less a battery. It just works when the sun is shining. Otherwise, it's just a piece of semiconductor. And the N-type can free off electrons, and the P-type makes holes where an electron can be stored or accepted. So N-type is called donor and P-type is called acceptor, and they're both actually uncharged in the beginning. And here we understand a little bit more how it is done. The N-type silicon is dotted with another element, which is often phosphorus. You can see here silicon is in this group where you have 4 valence electrons, and phosphorus has 5. So there's one loosely bound electron that can be used if there is a photon of enough energy that's gonna release this electron. And then you have a circuit, so the electrons can flow through metallic lines and do some work, and then they're gonna flow into the P layer. Physics teaches us that charges go from positive to negative, but actually, because they are electrons and electrons are negatively charged, they go from the N layer, from the negative part to the positive part. How is that for CCD sensors? The beginning of the process is actually the same. The CCD sensors react to light. Light frees some electrons and then has to be stored. And this is actually different to the solar cell. Here you can see the guys who invented the CCD. They got the Nobel Prize in 2009, but the invention of the CCD was in the 60s of last century. So it took the Nobel Committee 40 years to understand the importance of this invention. And the funny thing is, or the interesting thing, these guys worked for Bell Labs, and the people who produced the first useful solar cells also worked for Bell Labs, so it was the same company. Which can be understood, they're working with semiconductors, and the inventors of the CCD actually didn't plan to invent CCD cameras. They were working on a storage mechanism for electrons, and then they realized that it could be used as a photographic sensor. Here the CCD is shown, but I won't explain everything of that because I don't understand everything of that. But the most important thing is you have a lens, and that concentrates the light, and then a photodiode that transfers photons into electrons, and the electrons are stored, and then they can be read out. And in a CCD camera, the readout mechanism is at the periphery of the sensor, contrary to CMOS, where every photodiode is read out by itself. That's the difference, but we're gonna do that in a later video, actually, the CCD and CMOS sensors. But speaking about the mechanism that translates photons into electrons, they're actually quite similar anyway. For the CCD sensors, they also can be used at low light, which is not something solar cells are built for, and they can be cooled, which reduces thermal noise. But of course, being a semiconductor, it's not straightforward what happens when you cool them, because the electrons need energy to be used. People say that the signal is the same when you cool the sensor, but the noise is just lower. What are the problem of silicium-based solar cells? There are basically two problems, and they're connected with this mechanism here. In the valence band, you have electrons that can be used, and as soon as photons enter, they enter the conduction band. But they have to, energetically speaking, to jump from the valence band to the conduction band, and it needs energy. It needs some minimal energy that depends on the materials that you use in the semiconductor. And here they say, this is actually something I discussed in earlier videos and I didn't know back then, that if you have photons of a longer wavelength than this value, 1130 nanometers, the response is 0, because the photon doesn't reach the conduction band, so there are no electrons. The electron can't be released and can't be measured, basically. That's one problem. The other problem is that if the photon is too energetic, the electron will jump and be used, but it's rushing through the lattice, and it has to be slowed down, which means it gives off heat. And this is a problem for both solar cells and photographic sensors. Here it's shown that you can have different band gaps in semiconductors, or in these sandwiched semiconductors, and the band gap corresponds to a wavelength range, as we'll see later again. So what are possible solutions? One solution is use different materials that can be applied on thin films like cadmium telluride or CIGS, copper indium gallium selenide, and there are also some very new materials like perovskite. But basically they also have the same issue that you have a band gap, and depending on this band gap you have a wavelength range that they are very good at, and if they are too sensitive they will heat up, but they may be able to measure into infrared also and use more of the sunlight. The cadmium, some cadmium based solar cells have been invented very shortly after the silicium solar cell, actually in the same year, but back then it was cadmium sulfide and not cadmium telluride. And there are also broadband semiconductors that we discussed already in the first video about infrared sensors. For example, the colloidal quantum dot sensors, they're more sensitive to longer wavelengths and to a very wide range of photons. And also the InGaAs, the indium gallium arsenide semiconductors, they're very broad in their spectral sensitivity, but they will also heat up a lot because they can be excited already with shortwave infrared, and shorter wavelength light will make them hot actually. So the solution that the solar industry found was just use two solar cells on top of each other, and they can be specialized on different photon energies, or to say it differently, on different wavelengths of the light. For example, here you have a silicium cell and a perovskite cell, and normally the bluer one, the one for the higher energy photons, is on top, and the one for the lower energy photons is in the bottom. And this principle has been used also for photographic sensors. Foveon and later Sigma are developing sensors that are layered on top of each other. So you have the blue sensor on top, then a green sensor and a red sensor. And as you can see, the blue sensor is the smallest one and the thinnest one, and then the green in the middle and the red is the thickest one. They still have a bit problems separating the colors, and they found a solution to that, but the solution actually makes them less good for low light conditions. But Sigma is still working on these sensors. For example, they tried to make a full frame sensors, and so far they have reached only APS-C sized sensors. It's quite brave of this company that they use a completely different mechanism than everybody else. Everybody else uses this one where you have smaller sensors equipped with color filters. So you always have two green and a blue and a red sensitive cell packed together side by side and not on top of each other. I will also in a later video talk more about these Bayer things. And there are even triple cells on top of each other, so you have short wavelengths in the middle and longer wavelengths, as you can see here. So maybe the ultraviolet and a large part of the visual is been measured or used by the top cell, and then the middle is in the middle, and on the bottom you have the lower, the higher wavelengths, the lower energy photons. And this is an actual sensor that a company made, and they used, for the longest wavelength, they used a silicium cell and then two perovskite cells with different band gaps. So this one taps the highest energy, this one the middle, and this one the lowest energy, or corresponding to the longest wavelengths. But as you can imagine, this thing is quite complicated and quite expensive to build. So people are working on solar cells, and they're getting better and better. As you can see here, the cell efficiency, some experimental, these violet ones are more or less experimental cells. They reach almost 50% energy efficiency in the lab. But the ones best out in the field are still the crystalline silicium cells, because they're also stable and don't degrade much by sunlight, and they produce 20% of the, use 20% of the standardized sunlight. And the thin film technologies are shown here, the green ones, and they are almost as good as the crystalline silicium solar cells. And the emerging photovoltaics here work with lots of different mechanisms or substrates, and some of them have improved quite a bit already, like the perovskite cells, perovskite and perovskite tandem cells. So this is a summary, categorized into first, second and third generation of solar cells. And from the first to the second generation, you tend to use materials that are lower in the periodic system of elements, so in higher periods actually. But materials grow more scarce and are sometimes also toxic, like cadmium, for example. Also lead can be used for solar cells, and these are heavy metals. So the semiconductors are all in the same area of the periodic system. Starts with silicium, and then gallium, germanium and arsenide, things like that, and then indium and tin and antimony and tellur. But the further down you're in the periodic system, the rarer these atoms can be found in the Earth's crust, so they get more and more expensive. And the third generation of solar cells, some of them based on materials that are quite cheap actually, like polymers. But the question is a bit their stability, because if you take the sunlight with its ultraviolet, hard ultraviolet, then they could degrade quite a bit, and also water can degrade them. So they're still quite experimental. Some can be very efficient, like the 3-5 semiconductors. And this is another summary of all the different types. And here you can see, for example, gallium arsenide. They're very efficient because they also can use infrared, and the materials are still reasonably abundant. They're also stable. The only drawback is they're very expensive to produce. And this means that they are used in space, basically, where you need the energy and want to save on weight, because you have to start them with a rocket. But they're interesting for infrared astronomy, of course. Just still very expensive, even if you have just a sensor of half an inch or so. Thanks a lot for the attention.